Hi class, we are on to the next section, chapter 10.4. Today we're going to talk about the algebra of matrices. So basically what we're going to do is we're going to talk about how do we add matrices together, how do we subtract them, how do we multiply them, multiplying them by a constant, things of that nature, right? Powers of matrices, basically all the things that we would do with either a function or a number or a vector or any of those other kinds of objects that we do math on, right? So let's first talk about the easiest thing that we always talk about with two numbers, which is addition and subtraction. So we're not adding numbers. Again, we're adding or subtracting matrices. When we add or subtract, remember that addition and subtraction are basically the same thing. When you subtract two things, you're basically adding a negative value, right? So I really just talk about things, if you haven't noticed, in terms of addition, right? Adding two positives or adding a positive and a negative. That's really how we kind of approach subtraction, right? So if I want to add or subtract two matrices, they have to have the same dimensions. So remember, we talk about the size of a matrix in regards to its number of rows and its number of columns. Remember, rows first, columns second. So if I want to add two matrices or subtract two matrices, their number of rows and columns must both match up, right? So the number of rows of one has to be the same as the other, and the number of columns in one has to be the other as well. When we add these things together or subtract them, we do them component-wise, okay? So we said the same thing when we're talking about vectors. When I add or subtract two vectors, I add them component-wise, okay? You can actually think of two vectors as a matrix that has one row and then however many columns. So a lot of the stuff that well, pretty much everything we're allowed to do with matrices, we actually get to do with vectors as well. Because we just think about a vector as a one-dimensional matrix, right? One row with, you know, n number of elements, 3 elements or 2 elements. So it'd be a 1 by 2 matrix or 1 by 3 matrix, okay? So in general, if I want to add two things together, I take A plus B or A minus B, and this is our notation for a matrix, okay? This symbol here means I'm using a matrix. Aij represents that it has I rows and a j number of columns, again, row and then columns. And it's just saying that each entry is A. So it'll have entry A11, A12, A13, A21, A22, etc., etc. So this just means a matrix, okay? And it just kind of tells me what all the things inside of my matrix are. So it's just another notation for matrix, just like A is the name of a matrix. So what does this look like? Well, this is basically saying if I add two matrices together, it's the same thing as if I add the elements of those entries together, right? So the AI entry and the Bij entry, those get added together and create a new matrix, okay? So if we expand this Aij out, it looks like this, okay? So notice this is n by m because it doesn't have to be square, right? The number of rows does not have to match up with the number of columns. So again, m columns, n rows. 1, 2, 3 up to n for the rows. 1, 2, 3 up to m for the columns. So this is what A would look like. This is what B would look like. I'm either adding them together or I am subtracting them. So here, if I is 1 and j is 2, then that means I is 1 and j is 2. So A12 adds together with B12. That's what this notation means. Each entry that is identical in A as it is in B, those are the elements that get added. So here, the sum of these is I'm adding A11 plus B11. Okay, those get added or subtracted depending on what operation I'm doing. Same thing here. The first row, second entry, first row, second entry. I add those two numbers up to give me the new first row, second entry. So again, we're just adding them component-wise, just like we did with vectors. Okay, so let's do an example, because again, this can be very abstract and very kind of just maybe not make any sense at this moment. So if we take an example, let's say I have 1, 2, 3, 4, 5, 6, and here I have 6, 5, 4, 3, 2, 1. right? So if I subtract these together, it's 1 minus 6, 2 minus 5, 3 minus 4, 4 minus 3, 5 minus 2, 6 minus 1, okay? So when I'm doing these, I do them component-wise, right? 1 minus 6 is a negative 5, 5 minus 2 is a 3, right? So if I pick any one of these entries, that's how I find them. I'm just taking the exact identical place in one matrix, I find the next identical place in the other matrix, and I take those two entries and I, in this case, subtract them, right? 2 minus 5, those first row, second entries, first row, second entries, right? 2 minus 5, negative 3. We can also multiply a matrix by a scalar. So just like with a vector, if I multiply a vector by a scalar, every single element in my vector gets multiplied by that value. Same thing here. A scalar will multiply my matrix component-wise. So if C is a real value, C times my matrix A looks like this. I'm going to take C and I'm going to multiply it on the outside times every entry represented by Aij. That's the same as if I multiply C times every single entry inside of A. So what does that look like? I have C. I'm writing this out in its component form, and that's equal to me multiplying each entry times this vector C. So every element inside this matrix gets multiplied by the same value. Okay. An example of this is, let's go again, 1, 2, 3, 4, 5, 6. Multiply that times 2. That means every element inside of this matrix bumps up by a value of 2, right? So everything gets doubled. So instead of 1, 2, 3, 4, 5, 6, we have 2, 4, 6, 8, 10, 12. Right? So now let's talk about some properties of matrix addition and scalar multiplication. So these are just general rules, kind of similar to this. It kind of lets us know the things we're allowed to do when we have matrix equations. Okay, so the first is let S and T be real numbers. So again, these are going to act as our scalars. Whenever we say let this be a real value, that's going to end up being our scalar multiple values, right? A, B, and C are n by m. So notice they are not the same. They can be, but in this case, it's possible that they're not. They don't have to be. If I had the condition that they are n by n, then that would mean that the following conditions only held for square matrices. And so having two different indexes here means that they don't have to be square in this case. Okay, they can be, but they don't have to be. So A, B, and C are my matrices. This R means that they have real valued entries. So it could be pi on the inside, square root of 2. It doesn't really matter what's in as long as it's not complex inside, right, or imaginary. So S and T are real numbers, scalars. A, B, and C are my vectors, or I'm sorry, my matrices. So if I take a matrix A and a matrix B and I add them together, so again, this is assuming that, well, here they have the same dimensions, so they will match up and I can add them. I can actually switch the order around and add B plus A instead and get the same thing out. So this is what's called commutative. Okay. If I have a scalar multiple of A plus B, so again, I do the addition first and then multiply that sum by a scalar, then it's the same thing as if I were to multiply each matrix by a scalar, that same scalar value, and then add them together. So I can actually distribute my scalars across sums and subtractions. Okay. So if I have two scalars that I'm adding together and I'm multiplying that times a matrix, it's the same as if I were to distribute the matrix across the scalars. Right? D is that if I add A and B and then I add that sum to C, it would be the same thing if I were to add B and C together and then add that sum to A. So this is the associative property. Meaning it doesn't matter which order I add matrices together, as long as they all end up getting added together, right? S times T times A, so again, S times T is a new scalar, times A. It would be the same thing if I took only one of those scalars and multiplied it times A, and then I multiplied the second scalar times that scalar product. Okay, so most of these are pretty basic. They flow right out of the arithmetic of functions. So they're things that you guys are pretty much used to, right? So now we're going to talk about matrix multiplication, which is a little bit more involved. There's a little bit more to it. I suggest you guys review the dot product a little bit. The method in which we multiply matrices is basically we use the dot product over and over again. Okay, so if you don't remember what the dot product is, it's how we multiply two vectors and get a number out. Okay, so the dot product gives us a number. The cross product is the way that we multiply two vectors to get a new vector. So here we're going to do the dot product over and over and over again, and it's going to create all of the new entries in my new matrix. So when I multiply two matrices, I do get a new matrix out. But the method in which I get those entries in the new matrix is by using the dot product. Okay. So before we talk about that and we get into the actual algorithm, the process of multiplying, because at first it seems like a lot, but it's actually pretty straightforward once we get in the habit of it, we have to talk about whether or not we can actually multiply the two matrices. So in order for two matrices to be able to multiply, the dimensions have to match. And what that means is that the number of columns of one matrix has to equal the number of rows of the other matrix. Okay, so this leads us to a nice conclusion, or a difficult conclusion actually, which is that the manner in the order in which I multiply matrices together matters. Okay, which we'll talk about in just a little bit, right? So if the number of rows of one matrix matches up with the number of columns of the other, I can multiply them, but if I switch the order in which I multiply, they might not multiply together. So the order in which I decide to multiply things using matrices is very, very important. Okay, so what does that mean? It means that A times B does not always equal B times A. In fact, most of the time, A times B is not equal to B times A. It's a very special group of matrices in which these two things are equal, right? It's called the commutative group. So let's say that A is M by N and B is N by K. So remember, rows, columns, rows, columns. Then A times B will be M times K. So notice that the number of columns for this is N. The number of rows here is also N. That means I can multiply A times B. But I actually cannot multiply B times A. Now you might be saying, Professor Williams, what the hell is this? This makes no sense to me, which is fine. So let's go ahead and do an example. Okay. So I like this sort of little drawing here because it kind of lets you know whether or not you can multiply two things. So if you take A and you take B and you write their dimensions under them, the way that you know whether or not they can actually multiply is that the inside terms, right? So this column and this row, they're on the inside, they're next to each other. Those numbers have to match. Okay, they have to be the same. If these numbers are not the same, you cannot multiply A times B. And then what happens is when you do multiply A times B, these outside dimensions turn into the new dimensions of your product. So in order to multiply A times B, these two numbers have to be the same. Okay. And when you multiply A times B, the size of that new product is this times this. So this will be the number of rows and this will be the number of columns. So that's why it's nice to know how to say, oh, okay, this is the dimensions of A, this is the dimensions of B, because one, it'll let you know whether or not you can multiply them. And if you can multiply them, it'll tell you the size of the product they get out. Okay. So now let's talk about the actual algorithm of multiplying two matrices. If I want to actually multiply these things, I'm going to take the dot product where I'm using the row of A as a vector, and I'm using the column of B as a vector. Okay. And the row that I'm in here and the column that I'm in here will tell me what entry value I'm using in the product AB. So again, remember what I said about a vector is basically a matrix. It's a one-dimensional matrix, right? A row vector will be a 1 by, I don't know, 3 matrix if it has one row, obviously, and then 3 entries. That means it has 3 columns. Each one of those numbers would be a column. If we're looking at a row vector, then that could be, I don't know, a 3x1 matrix, for instance, if it has 3 entries, but it's in a column, so there's only one column in that case. So if I needed to multiply those two together by using the dot product, I could still do that, right? Because the dimensions would match. I'd have 3 for the row and have 3 for the column, and doing the dot product would give me a value out, right? So the way that this works is that if all the entries in A are A, ij, and all the entries in B are B, ij, then all the entries in AB are given by AB, ij, right? And so in order to find this entry, what I'm doing is I'm taking the row of A, so whatever I for A, whatever row, okay, remember I is row, J is columns, and whatever J column in B to create that entry. So now you might say, Professor Williams, this is very confusing also, so let's do an example, okay? So if I did the dot product with the second row of A and the third column of B, that'll create the entry in the second row, third column of my product. Okay, so here's a little diagram. This matrix is 3 by 3. This matrix is 3 by 3. So the number of rows match up with this number of columns. Okay, and so 3 by 3 and 3 by 3. So that means that the matrix it gets out is 3 by 3. So if I take the second row and this third column, okay, so dot product this, so this times this term times this term, this term times this term, and I add them together, right, the dot product. This will give me in this matrix the entry that is in the second row, so second row and third column. So second row, third column gives me this value, and that's how multiplying matrices work. So if I want to find this number, I would take the first row and multiply it times the first column to get the first value. To get the second, this entry here, which is in the first row and the second column, that entry right here, I would need the first row times the second column to get the entry in the first row, second column, right? So second row, third column gives me the entry that's in the second row, third column intersection. So let's do an example where we are finding each element by multiplying a matrix. Okay, so we're going to find A times B, where A is this matrix and B is this given matrix. Okay, so first things first is we got to check to make sure the dimensions match. So the number of columns here is 2, the number of rows here is 2, so we can multiply everything. Okay, so again, number of columns has to match with the number of rows in order to multiply. So what I'm going to do is to find the first entry in the product is I take this first row vector and this first column vector and I find their dot product. So that's going to be 1 times 3 plus 2 times 4. That'll give me the first entry, right? The entry in the first row, first column for the product. So note again that my matrix A is 3 by 2. My matrix B is 2 by 3. So the inner dimensions match up if I decide to go A times B, right? And that means that the matrix I get out is the outside entry, so 3 by 3. So I should end up with a 3 by 3 matrix when I'm done here. Okay. So if I multiply B times A, that means I move this to the other side. So the inner entries are 3 and the outer entries are 2 dimensions. I'm sorry. So then if I multiply in the other order, I will get B times A. And off top, you know that that is not the same because the dimensions are different. A times B is 3 by 3. B times A is 2 by 2. There's no way that those matrices are the same matrix. Okay, they don't even have the same dimension. So let's go through this again. So I'm going to take this first row times this first column for the dot product. So 1 times 3 plus 2 times 4. Okay, that gives me the first element in the first row, first column position for the product. For the next one in the first row, second column entry, I'm going to find the dot product of 1, 2 and this subvector for 3. Okay, so 1 times 4 plus 2 times 3. For the next one, I'm going to do the same thing. For the last entry in the first row, last column, I take this row vector times this column vector, and I find this dot product, so 1 times 3 plus 2 times 3. And that's the third entry. So I do that for the rest of these. For the second row, first entry, I'm going to take this row vector times this column vector. Okay, so 0, 3, 1, 4. Then for the next one's a 0, 4, 1, 3. Then this and this one, so 0, 3 times 1, 3. Okay, and then for my last one, I'm going to do the same thing, same order. So I'm going to use this, right, third row, so everything in the third row, this row times this column, then this row times this column, then this row times this column. So 2, 2, and 3, 4, 2, 2, and 4, 3, 2, 2, and 3, 3. Right? 2, 2, 3, 3. And so now, in order to actually find this out, normally I would do this in my head because it doesn't take a lot to go, oh, 3 plus 8, right? So 3 plus 8 is the first entry. So you can write them all out, but I really don't suggest that you write each term out. These you should generally be able to do in your head unless you have a very large size matrix here and here, and you have to do several terms dot product together. Most of the times you should be able to just be like, okay, 1 times 3 plus 2 times 4. So 3 plus 8. The next one is 4 times 4 plus 6. So that should be 10. The next one is 3 plus 6. So that should be 9. And then 0 times 3 is 0, 4. This should be 0 plus 3. 0 plus 3, right? So it makes it pretty easy once you've done it a few times. The first couple times, you'll probably have to write it out a few times until you like, oh, this is the way that it goes. But it's very formulaic. Okay. So that's how we multiply to matrices. Now let's talk about the commutative portion of that. So that was A times B. What would B times AB? So if we did the other order, okay, just for posterity to show that they're not the same. So the dimensions do match, right? I have 3 columns and 3 rows, so I can multiply them together. So I'm going to find the dot product. This is going to be 3 plus nothing plus 6. So that should be 9 for the first entry. For dot product of this with that, I should have 6 plus 4 plus 6, right? So 16. So 9 for the first one. The next one should be 16. There's no more rows, so now I go to the next row and I do it with this column. So 4, 0, and 6, so I should have a 10 here. And then 8 plus 3 is 11, plus another 6 should be 17, right? And that is how we do that. So a lot of times, you just kind of go one piece at a time. Go slowly because it's very easy to try to add everything together and forget that you're multiplying stuff. That's something I do quite often. So a lot of times I just go, oh, this is 4, and this is 3, and then this is 5, for instance. So I'll go 5 plus, or I'll go 4, or I'll go 4 and 1 is 5, and I'll do another 5, and I'll end up adding things. So just make sure you're going slow and doing your arithmetic correctly. Okay. So again, note that A times B is not the same as B times A. They, in fact, don't even have the same dimension, right? This is 2 by 2, and this is 3 by 3. Completely different entries, not even similar to looking the same, even when you're just looking at the entries, right? So let's talk about some properties of matrix algebra. So let S be a scalar, and let ABC be an n by n matrices, okay? Then from our previous definitions of addition and multiplication, we have the following, okay? If I multiply two matrices, right, so B times C, and then multiply that product times A, it's the same thing as if I multiply A times B, and then multiply that by C, except that this product AB needs to be on the left-hand side, right? If I multiply B times C and then multiply times A, B times C needs to be on the right-hand side. So again, remember what I did here. I changed the position of the matrices. And when I changed the position, right, here I had B on the left and A on the right, I got a 2 by 2. When I had A on the left and B on the right, I got a completely different matrix. So the order that the matrices are put in are important. So here it's saying that if I do B times C first, that's fine, as long as I keep A on the left-hand side. If I do A times B first, that's fine, as long as I keep C on the right-hand side. Then these things will be equal. Okay. If I have A times B plus C, A on the left, I can actually distribute A across as long as I keep it on the left. Okay, so I distribute it across to B, but it stays on the left. I distribute it across to C, but it stays on the left. Same thing here. I can distribute across from the right as well, but it has to stay on the right. C is on the right-hand side. C stays on the right-hand side for both of these. Okay. If I have a scalar times AB, I can apply that scalar first to one of the matrices and then multiply it across. It doesn't matter which one I multiply times that scalar. Okay, as long as I keep A on the left, B on the right.